Hello, welcome. In this lecture we look at another famous set of problems for using Newton's laws of motion to solve. This would be the infamous inclined plane. And an inclined plane is just a big wedge, so let's draw one in here. So we've got a big wedge here, and it is inclined at some angle theta with the horizontal. And we've got an object here, let's say a box, and we're going to say that there's no friction. We will eventually get to be able to deal with friction, but not this time. Let's start with no friction. So the one key for dealing with these inclined plane problems is normally when we do our coordinate system, we've got our x and y plane nice and neat like we normally see it. Don't do it that way. You can do it with your x and y coordinate system unrotated, but I don't recommend it. It is easier if we rotate our coordinate system and we go ahead and make it so that the x-axis is parallel with the incline and our y-axis is perpendicular to the incline. This simplifies our free body diagrams and simplifies a little bit of the component finding that we have to do. Alright, so this block right here, let's say, has a mass of m, and we want to draw a free body diagram for the forces acting on this block. So as always, we have the weight of the block, and the weight of the block is going to be going straight down, mg. And it always goes straight down. And the normal force on the block is going to be perpendicular to the plane. Here is our normal force. So those are two very, very important conceptual things to understand. The normal force shoots out perpendicular to the plane. The weight, as always, is going to be going straight down to the center of the Earth. So we have components on our weight force now. And I'm drawing these components on the weight force and not on the normal force because I've rotated my coordinate system. So in terms of our new rotated coordinate system, we have a component of the weight force that's going into the plane, which is in the negative y direction, according to our rotated coordinate system. So let's call this mgy. And we have a component of the weight force that's going down the plane. And we'll call this mgx. Now this object is accelerating down the plane in the positive x direction of my new rotated coordinate system. So it is that x component of the weight that is going to be causing the acceleration. The normal force and the y component of the weight are equal and opposite. And I know this because the block is not accelerating in this direction at all. We don't have any vertical acceleration into or out of the plane. We just have an acceleration down the plane. So like we did with forces in two directions, or like I tell my students to do with forces in two directions, we'll split this up and we're going to talk about the sum of the forces acting in the x direction, and we're going to talk about the sum of the forces acting in the y direction, keeping in mind, again, that x and y have been rotated. So in the x direction, we see that there's acceleration. The block accelerates down the plane. So the sum of the forces in the x direction are the block's mass times this acceleration. The sum of the forces in the y direction are going to be 0. As we said, the block is not accelerating into or out of the plane. And these y forces don't matter in this problem. We can safely ignore them when there is no friction. When we start to talk about friction, then the normal force specifically comes into play. So in the x direction, we just have mgx going down the plane. So mg in the x, so the x component of that guy. And it's going in the positive x direction as I've drawn it, this way. So we need to find that component, and here's where the angles come into play. We've got the slope of theta. That is our slope angle, and if we do a little bit of geometry, which I'm not going to show you here, we can prove that this angle right here between the weight vector and its y component is also theta. So to find mgx, we can take mgx and move him down here to complete our right triangle, and we get to use some geometry, trigonometry, sine, cosine, tangent to find out what mgx is in terms of mg. Mgx is the side opposite of theta, and mg, the original vector, is the hypotenuse of this triangle. So opposite and hypotenuse, we're dealing with the sine. So the sine of theta is mgx over mg. Doing some quick algebra, we see that it's mg sine theta for mgx. So we'll go ahead and replace mgx with mg sine theta. That's equal to the mass times the acceleration. Now something interesting happens. Our masses cancel out on both sides, and we have the standard equation. The acceleration down the ramp is just equal to g, the magnitude of the acceleration due to gravity, times the sine of the angle of inclination. And this is true for any inclined plane as long as there's no friction. The acceleration is equal to g sine theta down the plane. We don't care about the forces in the y direction. So let's use this information to do an example problem, and we'll see how this works. Okay, here's our setup for our example problem. We have a block sitting on an inclined plane, and the incline is 25 degrees, and the mass of the block is 12 kilograms. There is a 100 Newton horizontal force pushing the block up the incline. So let's assume that there's a person standing down here, and he's applying that force of 100 newtons, and he's pushing straight horizontally because he doesn't understand physics. And we want to see two things. What's the magnitude of the normal force acting between the ramp and the block, and what is the acceleration of the block? We're going to assume that that acceleration is going to be going up the ramp, but the person pushing might not be pushing with enough force for the acceleration to go up the ramp. We're going to rotate our coordinate system so that up the ramp is in the positive x direction, and perpendicular to the ramp is in the y direction. So drawing our free body diagram, we've already got the 100 Newton force acting on the block. We've got mg going straight down, and we've got the normal force going up. Again, we're ignoring friction in this problem. So drawing in the components of two different forces here. mg needs components. It's got a y component here, and it's got an x component going down here. We'll label them mgy and mgx. And our 100 Newton force also has two components because it is not going in the straight x and y directions. We've got the component of 100 newtons going up the ramp, and we've got the component of 100 newtons going perpendicular to the ramp. So let's just go ahead and label this 100x and 100y. So there is, I don't want to name it 100x and 100y. That could get confusing, so let's change that. We're going to call it px and py, standing for the push. So this guy would be px, and then this guy would be py. I like that better. All right, so we've got our free body diagram, and we're going to look at the sum of the forces acting in the x direction. And we're going to assume that this thing is accelerating in the x direction. So we've got m times a, and we've got the sum of the forces acting in the y direction. And we're going to assume it's not accelerating at all in the y direction. Let me be a little specific here. Let's put an ax, just to show that it is accelerating in the x direction. Let's throw in some forces here. Let's see who's acting in the x direction. We've got px acting in the x direction, in the positive x direction, so the x component of the push, minus the x component of the weight going down the ramp. And that's it for forces acting in the x direction, or components acting in the x direction. So that's equal to mass times a sub x. Over here in the y direction, we've got the normal force going up. We have py going into the ramp. We also have mgy going into the ramp. And those are going to equal 0. So reminding myself, I'm solving for the normal force first. So we're dealing with the y's on this side, it looks like. So the normal force then is going to equal, this was py plus mgy. And I'm going to need to find those components of those forces. So going back up here, we've got to look at some angles here. This angle right here would be 25 degrees, as would this angle right here, 25 degrees. So py is going to complete my triangle. It's the side opposite, so we're looking at the sine. So py is going to be the force push times the sine of theta. And mgy is this red vector right here. And we see that he is the side adjacent to that 25-degree angle. So side adjacent is going to be cosine. So we've got mg, that's the hypotenuse, times the cosine of theta. That's going to equal my normal force. And we know the magnitude of P is 100. We know that theta is 25. We know the mass is 12. G is 9.8. So at this point, we can plug in numbers and solve. So putting those in, we've got 100 times the sine of 25 plus 12 times 9.8 times the cosine of 25. Let's put that into the calculator, making sure that you're in degree mode in the calculator. And to 3 sig figs, my calculator is telling me that it is 149 newtons that the ramp is pushing out with. And if we think about that, it makes sense because we've got the normal force up here is counteracting the y component of gravity, and it's also counteracting that y component of the push. The worker is pushing the box into the ramp a little bit. So the normal force has to counteract that as well. Doesn't make much of a difference, doesn't make any difference when there's no friction. It's going to make more difference if we account for friction. Now we're going to solve for the acceleration, and the x side is untouched. So let's work on the x side. Over here we found that py was p sine theta, so px has to be p cos theta. And also over here on the right-hand side, we found that mgy was mg cos theta. So that means that mgx is going to be mg sine theta. And that's equal to m times the acceleration in the x direction. Solving for the acceleration then, we divide both sides by m. M cancels there. And again, we know p, we know theta, we know m, we know g. So we can plug in numbers and solve. So the numbers we've got are 100 cos 25 minus 12 times 9.8 times the sine of 25, all divided by 12. And that's going to equal the acceleration. Again, putting them into the calculator. To 3 sig figs, my calculator is telling me 3.41 meters per second squared is equal to the acceleration. And it's lovely that it's not greater than 9.8, because that would be a really, really big, hard push going up the ramp. So it's definitely going in the positive x direction, because it gave us a positive 3.41. And it's not a crazy big number or a crazy small number, so it seems pretty reasonable. So there we have it. And again, going back up, the keys to this problem: rotate your coordinate system so that the positive x direction is going in the direction of motion of the object, in this case up the ramp. The y direction is perpendicular to the ramp. Draw your free body diagram. That would be the vectors in blue on our diagram. And then draw in the components. Anything that's not going purely in x or purely in y, draw in those components and show the angles. You're going to use those components down below. Then figure out what the sum of the forces in the x direction are doing to the object. In this case, there's an acceleration. What the sum of the forces in the y direction are doing to the object. In this case, it's 0. Plug in the forces that are acting, or the components of the forces that are acting in the x. Plug in the forces and components that are acting in the y. Solve for the unknown. There you have it. Have fun. See you later.